So, welcome to problem solving session for Introduction to Group Theory course. I am Siddhi Balu Ambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 2, that is basic properties of group, subgroups of a group, subgroup generated by subsets of a group, group of integer modulo n, and some elementary number theory. Okay, so let us start with our first question, that let G be a group, then which of the following statements are correct? This is basically, we have to check whether these statements AB square belongs to H for all A comma B belongs to H, for some subset H of G implies H is a subgroup of G. Second statement is, if H order of H is order of G minus 1, then H is a subgroup of G. Third statement is, if order of H is order of G minus 1 and order of G in this case is greater than 2, then H is not a subgroup of G. And if H is a proper non-trivial subgroup of G, then mod A, order of H is equal to order of G minus 1. So we have to check which of the following statements are correct. So we will see. So whatever statement we feel is true or false, or whether it's true or false. If it is true, we will try to prove it. If it's not true, we will give a counter example for that statement. So what about the first statement, whether it's true or false? Here what they have said is that H is a subset of G such that AB inverse belongs to H for any given A and B in H. So does this imply that H is a subgroup of G? Any guesses? Whether it's true or false, and what are your inputs for this statement? See, first of all, H, what they have, so in this statement, they have said that H is a subset of G, that's it. They have not mentioned whether this H is a non-empty subset or not. So if I take empty set is equal to H as empty set which is contained in G, then H is not a subgroup of G, right? For subgroups, I need to have identity in the set. And this empty set, which is also a subgroup of G, subset of G, which satisfies these conditions. So see, I mean, this AB square belongs to H for all AB in H. So when I say this, I need to have a subset of H, which contains elements A and B. And it should satisfy this condition that if A and B in H, then AB inverse must be in H. But here, if I take H to be empty set, then in that case there are no A and B's in H. And then this statement is, I mean, this is, I mean, there is nothing to check whether for given AB in H, whether AB inverse is in H or not. So this statement becomes vacuously true. I mean, the if part. And then, but this does not give me that H is a subgroup of G, because for H to be a subgroup, I need to have identity inside H. The identity of G, the group identity of G must be inside H. This is not happening when I consider H to be empty set. So that's why this statement here is not true, because here they have not said that H is non-empty set. But this statement is true if we put this condition that if here I can say since E doesn't belong to H. Okay, this is just for the, but we have this result or whatever theorem or proposition, whatever you want to call it, that if H is non-empty subset of G such that, sorry, then for all A comma B in H, AB inverse belongs to H if and only if H is a subgroup of G. This non-emptiness plays the role. Okay, so we will prove this statement instead. So this is completely, I mean, this is wrong because they have not mentioned that H needs to be a non-empty subset of G when we start to consider this statement. Okay, so but for H non-empty, this statement is true, and in fact, this is if and only if statement. That if H is a non-empty subset of G such that for all given AB in H, I have AB inverse in H, then my H is a subgroup of G. Okay, so let us prove this. The first part, proof. Let us prove this part, that AB inverse, given that AB inverse belong for all A, B in H, AB inverse belongs to H. Okay, so and to show what, that H is a subgroup of G. Okay, and so first associativity. So note that associativity condition, that if I need to check that whether A, B, C is equal to AB into C or not. But anyway, from the inherent property of G, this ABC is anyway ABC, since ABC belongs to H, which is subset of G anyway. So this comes from the restriction of G on H. Okay, so, and the second is identity. So identity. So since H is non-empty, there exists A in H, right? So by given condition, this A into A inverse belongs to H. But note that this multiplication A inverse is multiplication from my group G. So this A inverse is E and this belongs to H. So identity is there. And now third is inverse, which we need to check. And since E belongs to H, and if I take A belong, so let A belongs to H, and since E belongs to H, this E into A inverse belongs to H. A inverse is there from group G. I need to check whether this A inverse is also inside my H or not. Okay, so when we talk about subgroup, the inverse which we have of a given element A in H is exactly equal to the inverse we have for A in group G. So that's something we need to keep in mind. I mean, the operations, the identity, the multiplication or addition, whatever we are defining on H is inherited from G. So inverses and identities remain same in H. So this E into A inverse belongs to H from given condition since AB's inverse belongs to H. So that's why this A inverse belongs to H. Okay, so A is H. A, so for any given element, we have associativity. I mean, we have associativity for the elements of H. We have identity belonging to H. We have this EA inverse. Sorry, for any given A in H, we have A inverse belongs to H. So it satisfies all the conditions of being a group or subgroup of G. So here we used the fact that it is subgroup of G, sorry, a subset of G. And this identity AA inverse, this is operation from G. Okay, so that therefore H is a subgroup of G. And now this part is anyway holds. H is a subgroup. H is a subgroup given that H is a subgroup of G to show that AB inverse belongs to H for all AB in H. But yeah, if I take any AB in H, this since B is in H, B inverse belongs to H. So since A comma B inverse in H, since H is subgroup, and so these imply AB inverse belongs to H since it's a binary operation closed under binary operation. Okay, since it is subgroup, all the product of elements of H belongs to H again, since H is subgroup. Any doubts here? Whatever we did here, and the first part, that why the statement is not true when I consider H to be an empty set. If 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 there is any doubt, please let me know. Otherwise, I will move ahead to next question. I mean, next question means next option. Is this okay? If okay, I assume it's okay. Now the B part. B part they are asking is if H, if order of H is order of G minus 1, then H is subgroup of G. And when they are writing this statement, they are only considering it as a subset of G. Okay, so we can work with any subset of G which we want. And so any guess whether this statement is true or not? Any guess? Not true. So do you have any, so as suggested by someone, Kumar, that it's not true. true, that it's not true. So can we give one counter example? Do you have any counter example in mind? Or it seems that this is not true?
Ma'am, Z5.
Z5, and what will be my uh, and what will be my H? What H would you like to take? So yeah, I mean we can take any, not any, but we can take good enough subset of H. So for example, if I take H to be this 1, 2, 3, 4, this has cardinality 4, right? But it is not subgroup because I do not have identity here. So any subset with -1 did not give me subgroup of G, since, sorry, 0 bar doesn't belongs to H. Is this okay? We can do this with any group. Take a group, remove its identity, and whatever set is left, it has cardinal, I mean, any finite group. Whatever set is left has cardinality 1 minus the, I mean, the order of group -1, and that set won't form a group under the same inherent operation from G. Okay. Is that okay? I mean, G be finite group, any state finite group, then G minus identity has cardinality mod G -1, but H is never a group, or H cannot be a subgroup of G, as E does not belong H. Okay, so this you can keep in mind. Is this okay? So this statement is false. This B, that order of H -1 there. And now this statement, it is kind of similar statement, but here what they have said is that order of G greater than 1, sorry, greater than 2, and H, if that is the case, then H is not a subgroup. So now they are talking about H being not a subgroup of G. So what they are saying, that if cardinality of G, H is cardinality of G -1, and order of G or cardinality of G is greater than 2, strictly greater than 2, then H is not a subgroup of G. This is the statement now. And here this order of G greater than 2 plays a role, because if I take G, what they're saying is now that if H has size less than 1, and then H can never be a subgroup. So if I take order of G to be 2, and this is my H, I take just E, which has order G -1, but this is a subgroup. So this violates this statement. If I take G to be equal to 2, and G is order of G is 1, I mean, then in that case, this empty set doesn't make any sense. But I mean, it's not anyway subgroup, or we don't have to go to that. But when G is 2, the order of G is 2, that in that case, I can take this H is equal to just identity element, and that will definitely form a subgroup of G, and which I mean, which makes this statement false. So in order to keep it, uh, I mean, to have this statement true, we need this condition here, that mod G greater, order of G greater than 2. Okay, so we have to prove this. So how to go with this? That, so note that if So suppose order of H is G minus 1. Let order of and G is greater than 2. Now suppose H is a subgroup of G. So we know that if H is a subgroup of a finite group, that then in that case this order of H divides order of G. This is clear, right? So from this what I get, that order of this order of G minus 1, no, since order of H is order of G minus 1, this statement holds. And this implies that G, what will be the cardinality of G then? That G minus 1 divides G. This implies order of G is less than equal to 2, right? So which is contradiction since order of G is strictly greater than 2. Therefore, H is not a subgroup of G. In fact, this is equal to 2. Is this okay? Any doubts here? This is simple. I mean, number. Okay, no doubts. Okay. I mean, these are basic properties of integer division and so on. So I hope that's okay. And the last statement. So this one is true. Okay, we just proved that this is true. That if this happens, then this doesn't hold. It contradicts the size of group which is given to be greater than 2. And now the last statement, that if H is a proper non-trivial subgroup of G, then order of H has to be order of G minus 1. But that is anyway, we know it's not true. If H is a proper non-trivial subgroup of G, then H is order of G minus 1. Order of H is order of G minus 1. So any guesses for this? I mean, this is not true because we can take any group, right? So let us take the group which we considered last time. This K4, E, A, B, and this A was AB. And here everything was A square, B square, C square, everything was, not everything, I mean A, B, C square were 1. So if I take H to be this, right? This is group. This is subgroup of G. This is subgroup of G, right? A square is E. A square, multiplication, division, inverse, multiplication, inverse, identity, everything is there. Okay, so this is subgroup. But order of H is 2, which is definitely not equal to this G minus 1. This 2 is equal, like, order of H is 2 is not equal to G minus 1, which is 3. I mean 4 minus 1. Okay, so this statement is, that's why not true. The only statement true here is this. And this statement is also okay if we said that if we set the condition if that H is a non-empty subset of G. Okay, we proved that in the case of non-empty subset of G, this statement holds. And in fact, this is if and only if statement. I hope this was okay. Any doubts, please let me know. Okay, now, if doubts, please let me know. Otherwise, I will move to next question. Let A, comma B and M be positive integers. Okay, and then first is that again we have to check whether the following statements are true or false. Check whether true or false. So first is that if GCD A comma M is 1, which is equal to GCD B comma M, then GCD A plus B comma M is also 1. Okay, so I'm writing the statements. Meanwhile, you can try to think whether this statement correct or not. And if not, then try to find the counter examples. And if correct, then try to obtain a proof. GCD of B by A comma M. MA. Yes, exactly. Those are the exact numbers which I had prepared. Okay, so just a second. Let me finish this. And okay, so these are the options. And as suggested by Amit, we can take A to be 2, B to be 3, and C to be 5. Then in this case, GCD of this 2, comma 5 is 1. GCD of 3, comma 5 is 1, but GCD of this 2 plus 3, comma 5, that is GCD of 5, comma 5 is 5, which is definitely not equal to 1, which was asked here. So this is not correct. And for A minus B, we can do the same, right? These three numbers which we just have to choose A, B, and M smartly. And we can choose A to be 5, B to be 2, and M to be 3. Oh, this M here. Then GCD of A, comma, this 5, comma 3 is 1. GCD of 2, comma 3 is 1. But GCD of 5, comma 2, sorry, 5 minus 2, comma 3, which is GCD of 3, comma 3, which is definitely not equal to 1. Okay, so this second statement is also not true. Third one, any guesses here? We have again GCD of AM, BM 1, and A divides B in this case. And here we have these numbers. B divides A, the GCD of, so since B divides A divides B, we have this B minus A as an integer. And then they are saying this when A divides B, its GCD with MA is 1. Can we find that? Can we have such a example, or is this true? Any guesses for the C part? We what A, B, and C. So we are given, we want elements such that GCD of AM is 1, GCD of BM is 1, A divides B, and I want GCD of this B by A comma MA to be 1. Is this possible? What A, B, and M I need to choose? We can choose this basic, not basic, but this easy. We want some A divides B. So take this. BM needs to have GCD. So AM and BM needs to have GCD 1. So 2, 3 and this had GCD 1. And also I have this 2, 3. 4, 3 has GCD 1 and also 2 divides 4. So this is what? MA, right? So 4 by 2, and here I have 2 into M is 3 and A is 2, which is 1. Okay, so therefore this GCD of now 2 comma 6 is 2, which is not equal to 1. So therefore this does not hold. Okay, for this to hold, we can choose examples where this actually holds, but we want to check whether the statement is true or false. So even if one example where the statement doesn't hold, it's false for us. So now we have to check the last statement. Is this true? These two statements are okay. Okay, there are many examples where this holds, but I would definitely want you to go through this one, and I'll write this. Try to find ABM such that this holds. Okay, that C holds. Now the D part. We have given that GCD A comma M is 1, GCD of B comma M is 1. Then we have to show that this statement is true actually. So we'll check. We'll try to prove that this holds. Okay. So we have to now prove that GCD of AB comma M is 1. So since we know that since GCD of A comma M is 1, this implies there exists P comma Q in Z such that AP plus MQ is 1. And similarly, GCD of B comma M is 1. These imply there exists R and S in Z such that this RB plus S, sorry, RB plus MS is 1. Am I making some mistake here? BRMS. Okay, and now I have to find this. So if I multiply these two sides, this AP plus MQ, BR plus MS is equal to 1, then what I get? This AP, let me just write it properly. ABPR plus AMS plus MQBR plus M square QS is 1. So here AB into PR plus M into this AS plus, there is some, I missed something, I guess. Yeah, AP. APS plus QBR plus MQS is equal to 1. So I have these integers PR and this such that AB plus M is, I got these elements in Z such that AB, if I call them whatever, let me call them U plus M into V is 1. So I can say that GCD of AB, comma M is 1. Okay. Is this okay? We got the integers. So this statement here,
Ma'am,
mhm.
we have to show here one is the minimum positive integer making this linear combination.
So see if they suppose if GCD of this AB comma M, if there exists some D such that if D divides AB and D divides M, then this AB alpha plus this M beta, this D will always divide this.
Okay, ma'am.
Okay, so if this D is greater than 1, this will always happen. So once I have 1 here, this gives me that GCD of these two element is 1. This we can say only in terms of 1. Okay, this uh, going from here to here, sorry. If I have something of this kind, that just because this AB alpha plus MV beta, sorry, M beta, if it's some D, and if this D was something which is not equal to 1, then we can't conclude that GCD of this AB and M is D. Okay, but
Okay.
since it is 1, we got the expression said that this is equal to 1, that's why we can say that. If this D was not equal to 1, this need not hold. Okay, need not hold. Because see, I have this, if I do this, that 4 into 1 plus 2 into 2, no, not this one. What is GC? Yeah, suppose I take GCD of 5 and 10 is 5. So if I take 10 into, wait, 10 into 1 plus minus 1 into 5 is 5. Okay, but I can just multiply this with these numbers, right? And 5, and I get 10 here. But this 10 is not GCD of 5 and 2, 5 and 10 here. But since it is 1, we can say this, that GCD will be 1. This is especially for 1 it happens, that once I have linear combination of two integers which is giving me 1, then I can conclude that their GCD is 1. Otherwise, we can't say that. This example here, everything here, all this had GCD 1. So this is for GCD 1. We can't say this for any other GCDs. with this statement at least. Is this okay?
Okay, ma'am.
Yeah. Let me just shift this here a little bit. Let us go to now next question now. I hope this is okay with everyone. If there is any doubt, please let me know. I think we solved all the four options, right? This one holds. This one is true. And this one we can, only, let me write here. Only if G, only to on, how to put this? Can be concluded only in case of GCD1. This is still not a correct way to write it, but yeah. So let's move to this next question, that let G be a group which of the following subsets of subsets H of G form a subgroup. Subset H is a subgroup of G. So here, what? Okay, let me just write the options first. H is such that A belongs to G such that A power n is 1 for some n belongs to n. B is G is abelian, and this H is now this group. A belongs to G such that A power n is 1 for some fixed n. Okay, and C is given n in n, and H is A belongs to G such that A power n is 1. And final is that H is of this form: A power m, B power n such that mn belongs to Z for some fixed A, B in G. Okay, so any guesses for this, whether it's true? The first statement. So let's start with first one. Any guesses here or suggest? Any input from your end, whether statements are true or false or what is happening? So here what they are saying is that if A belongs to G, then A power is equal to first one. So let us start with first one. How H is defined, that it is all the subsets such that A belongs to G such that A power n is n for some n in n. So what this statement actually means is, see, we are considering all the elements from G such that A power n is equal to 1 for some n in natural number. So what does this mean? That all the elements of H are such that they have finite order in G. Okay, G is given just a group. They have not said that G is my finite group or whether it's finite, infinite, or anything. They just said that G is my group and it's just a group, and H is just subset which collects all the elements of finite order. So this definitely contains E. Okay, so this, if I it definitely contains the multiplicative identity or identity, the identity of group. And if A belongs to G, then definitely A inverse would belong to G, because see, A inverse power, if A power n is a G, then A inverse power n will also be, sorry, not GE. You can check this because A power n, A inverse, A inverse is A inverse A. So when I do this, A inverse power n, this is A power n, A inverse power n, which is E. So this becomes E. So identity inverses and everything is okay, but does this group, sorry, not this group, but is H closed under the multiplication of my G? So what they are asking is whether I take two elements from H. So elements from H have finite order. So their product or their addition will also be in H or not. Means will they have finite order or not? That's the question which this option is asking. That is product always of finite order? See, if G is, first thing to observe is that if G is abelian, then if A power, what to say? If A power n is E and B power m is E, then AB power, if I take just this mn, then since G abelian, this A power mn, this will be B power mn. And this will be E into E, right? That is okay. So if I want to find a counter example, we have to look for a group is uh, which is infinite and is not abelian. At least we have to search for those kind of groups. Because see, if the group is finite, then for some n, this will hold, right? The order of group is finite. So each element has finite order. So if I want to find a counter example where the order of element is not finite, then the group must be not infinite. That's like understood. And secondly, for in case of abelian, this holds. So we need to find an infinite group which is not abelian. Okay, so any guess what to choose? Not, we can choose this one, that let G be GL2R. Okay, this is infinite group. That's not a problem. And now I need to, and this is also not abelian. So I take this A to be this 0, 1, 1, 0, and B to be this 1 by 2, 0. Sorry, not this 0, 1 by 2, 2, 0. Then what is order of A? Let us check what is A square. This is 1, 0, 0, 1. So this is identity. Okay, or let me call this I as. And what is B square? Let us find the order of B. into 0, 1 by 2 to 0. 2 to 1, 0. This, okay, this is 0 and this is 1. This is again identity of GL2R. So we have A square, B square to be 1. But what is A into B? It is this 0, 1, 1, 0, 1 by 2, sorry, 0, 1 by 2 to 0. And this is this 2, 0, 0, 1 by 2. You can check this. This is just this elementary matrix which is shifting the rows. So it is this. And what is order of AB now? Do we have thus there exist n in such that E, or what is my identity? Does this hold? No, right? Because AB square is what? This is 2, 0, 0, 1 by 2 square, which is 2 square 0, 0, 1 by 2 whole square. Okay, so in general, for any n, this holds 2 power n, 0, 0, 1 by 2 power n. Since we are in diagonal matrices, just diagonals get multiplied component wise. Okay, so this is there. So this is not equal to identity for any n in natural number. Okay, so that's why this is not a group, because it is not. So H is not a group as it is not closed under multiplication or group operation. Is that okay? Is there any clear? The multiplication was a problem. That's why this is not sorry. That's why this is not. Now the second part is that G is abelian and A. Wait, let me write the second part. B. G is abelian and H is A in G such that A power n is 1 for some fixed n. So any guesses whether this will be true? Okay, so let us see this, that let A comma B in G, I mean C, A power n is 1. Again, it satisfies all these conditions. The identity will be there because n is fixed. Okay, so if E power n is anyway E, so E belongs to H. Second, if A power n belongs to, so if A belongs to H such that A power n is E, then A inverse power n is also E. Similar argument as we did here, this argument. So therefore A inverse belongs to E. And So identity and inverse is not a problem here. So let us check for the multiplication. So let A comma B in H. So what is AB? So we want to show that AB belongs to check AB belongs to H. So what does this imply? That is to check that A B power n is equal to 1. That is A B power n is equal to 1. That's it for n. For given, not for given n, I mean n is fixed. So AB power n is 1. That's what we want to check. So what is AB power n? It is A power n, B power n since G is abelian. So, but A power n, since A, B belongs to H, A power n is 1, that is identity, B power n is identity, so it is identity. So, therefore, A, B belongs to my H. Okay, or if you do not want to check it like this, we can do this. We can take this AB in H, since B in H implies B inverse in H, and we proved this, right? If I take A and B from H, if AB inverse also belongs to H, then H becomes subgroup. So let us see this, whether AB inverse belongs to H or not. So this is again this, and identity into identity, which is again identity. So therefore AB inverse belongs to H for all A, B in H. Therefore H is subgroup. So either we check all these conditions, that identity is there, inverse is there, and for the multiplication is there, and associativity will be followed from our group inheritance. So that's not a problem. Uh, I mean, in such cases, Uh, so either we do all these three conditions, or we just use question 1, option A result. Okay, and we can either do this or do check all these three conditions. But I hope this is clear that if G is abelian, then this forms a group. Okay, so this statement is now true. And now this, that given n in n, A is in G, A power. So when they write this, it also means that n is fixed. Okay, so given n in n, H is such that A in G, A power n is 1. So again here this n is fixed. Okay, when they have written that n, we are choosing n in n. Okay, so any guesses again? If we have two elements with the same order, does that mean that their product will have the same order? Not order, I mean, mm, not about order. I mean, what they say is that if A power n is E and again B power n is C, does that imply that AB power n will be E? This is the question again here. And this is exactly what we did in our first. So here what we had that A power n is 1 for some n, for some n. Here what they are doing is that they are fixing the n and they are collecting all the elements of that order. And they are asking whether, not order, I mean, they are collecting all the elements such that this nth power of that element is identity. And they are asking us to check whether this forms a group or not. But this is not true because we can again choose the previous. So now what we can do is, now again we will take this GL2R and fix n is equal to 2. And earlier this A which we had, order of, I mean, A square was this identity, And this B, which was this was also identity, if you remember. Okay, but this AB square, if we try to find what AB, we know it is 1 by 2, 0, 0, 2. So AB square is what? 1 by 2 square, 0, 0, 4. That is 1 by 4, 0, 0, 4. This is not, definitely not an identity, not the identity. So therefore, this is again not group, not subgroup. Okay, so this is again not subgroup. And now the final one. Fourth, not the part, that if H is of this form, A power M, B power N, such that M comma N in Z, and A and B are fixed for some fixed A comma B belongs to G. In any guesses? First of all, see that what this H is, it contains all the element of this form, AB power N. Okay, so but note that if, we already are very, see, if I take this A power M1, B power N1 in H, and this A power M2, B power M2 in H, then note that this A power M1, B power N1, B power N2, this need not be equal to A power R, B power S, for some need not be. Not necessarily. For some R, comma S in natural numbers or integers for that matter. This need not always hold. You can again create some examples and check that this does not hold. For example, if you take this, I won't do all this power multiplication, but check with this A. A, you can take this, again G to be this GL to R. Infinite non-abelian group. Okay, and B to be this 0, 1, 1. And see how, if I take this H to be this A power M, B power N, such that M N in Z, check how this happened, like whether every element of this sort, when I take multiplication of this A power M1, B power M1, whether if I take product like this, can I always present it like this or not? Sorry. Okay, whether this always happens. This won't always happen, okay? We can have sufficient power or some better matrices where this need not hold, okay? We cannot, not cannot, but we might not be able to express this in this form. Okay, please understand this. If this was abelian, then this would definitely happen. If A, B, N1, and this A power M2, B power N2, and then this becomes A power M1 plus N2, and this becomes B power N1 plus N2, if abelian. if abelian, then this happens. But this Gl2R is not abelian. And not only this, I mean, for here, order is not playing any role. So maybe you can try to find this in group with finite order. That would also work. That's not a problem here. The order is not playing any role. So you can very well choose some group of finite order and try to find A and B such that when I take their product of this form, then do not give me some element of this form, A power R or B power S. Okay? Try to find such examples. Okay. So this is not true. You can find the examples with the explicit. When the example is given, you can calculate I mean, you can do the calculation to see that this statement does not hold. Okay, so let me move to this next question now. That let H1 and H2 be two cyclic subgroups of a finite group G. If G is finite, then we have to check which of the following statements are true. We have to check which of the followings are true or not. So the subgroup generated by is cyclic. And P is that if G is cyclic, then the subgroup generated by H1 and H2 is cyclic. And if GCD H1 comma H2 is 1, then H1 intersection H2 is identity. And fourth one is the D part is that we always have H1 intersection H2 to be identity. So we have to check these statements. First one is that subgroup generated by H1 and H2. So when I say subgroup generated by H1 and H2, it means I also consider the products of this element. Okay, so I take the union of these two elements and generate a subgroup from them. So if I take H to be subgroup generated by H, means H is all H1, H2, says that H1 in H1 and H2 in H2. And this is not the only thing. Let me just write this. H2, HG, H1, G1, H2, G2, H2, G, such that H1, H2 in H, G1, G2 in G. All the possible multiplications of elements of H1 and H2. And they make sense because they both are subsets and subgroups of G. And so they are elements of G, and they have this product is well defined there. So this makes sense. And if I have this, I have to check whether they form subgroup or not. That's not is asked here. Here they say they are asking whether subgroup formed by this element is cyclic or not. So cyclic is the main condition which I need to check here. So do you have any example in mind, or this statement is true that if I have H1 and H2 cyclic, then the subgroup generated by all their possible products and everything, this new subgroup is always cyclic. Do you have any example? Or this statement is true? If true, then how to prove this? Not H. So if we want to find some counterexample, we have to start with the group which is not cyclic in the first place. Okay, so that we can have this non-cyclic condition to somehow. Okay, so any suggestions? So let us take this group. Let G be S3. It's not cyclic. And H1 we take this E1, 2, 3. I hope you know what this cycle represents and what it means. Okay, we did this last time. And this transposition. We are taking these two, H1 and H2. Both are cyclic. These are generated by this. And here this one is generated by 1, 2. Okay. So any suggestions? I mean, any. So we just have to check this H generated by this H1, H2. So see, if I take this element 1, 2, 3 and multiply it by this 1, 2, what will it give me? 1 here going to 2 and 2 here goes to 3 and 3 here goes to 3, but 3 here goes to 1. So this is giving me this element 1, 3. Okay. Now if I take this 1, 2, 1, 2, 3, what this will give me? Here 1 goes to 2, 2 goes to 1. So 1 is as it is. Now my 2 goes to 3, 3 stays there. And now 3 here goes to 2. So wait, are we doing this okay? 2 here goes to 3, 3 here stays. Here 3 here goes to 1 and 1 here goes to 2. So yeah, 3 goes to 2. So this is correct. So this is just this cycle, 2, 3. Okay, so what we have is, and see, here H1 and H2 also have E. So all these elements, this 1, 2, 3, 1, 3, 2 and 1, 2 are already there in my new group H, because E into elements H belongs to this new group H, and E into G belongs to H, for H belongs to H1 and G belongs to H2. Okay, so this is there. That's not a problem. And these are two new elements which I got. Okay, so collectively, H now has this E, it is there. 1, 2 is there. 2, 3 is there. 1, 3 also is there. 1, 2, 3. And this 1, 3, 2 is also there. So this is entire S3. And this is not cyclic. Okay. So that's why if F1 if I have two cyclic subgroups of given group G, subgroup generated by them need not be cyclic subgroup. Okay, so this statement is false. Now this B part, the B part says that if G is cyclic, then subgroup generated by H1 and H2 is cyclic. Okay, so B part, that if G is cyclic, then subgroup generated by H1 and H2 are cyclic. Any guesses here? This is true. Here we are asking whether subgroup generated by H1 and H2 is cyclic or not. But what I will do is we will prove this general statement that if G is a cyclic group, then every subgroup of G is a cyclic group. So we will prove this, that we'll prove this result, that if G is a cyclic group, then every subgroup of G, subgroup H of G is cyclic. Okay, so this is even general statement. So here my G is cyclic and H1, H2 are cyclic, and whatever subgroup it generates, let it be G, let it be whatever, it will be cyclic. What we are proving here is stronger, that given any G cyclic, its subgroup always will be cyclic. Okay, so let us try to prove this. So first one. So proof. So if H is this identity, or if H is A, which is just G, so say then it is cyclic anyway. Then it is cyclic. That's not a problem. Because G itself is a cyclic, this E is a cyclic generated by E. That's it. But if now, so now suppose H is proper subgroup of G. Okay, so what we do is then there exists a minimum positive power of A such that A power M belongs to H. This exists. See, if A belongs to H, then again it becomes the whole G. Okay, so this positive power of A, in fact, we can assume it to be greater than equal to 2 or something of that sort. Doesn't matter. We don't need to mention it here. But if it is not E or it is not the entire G, there exists a minimum positive power of A such that A power M belongs to H. And this minimum power, okay, please keep this in mind, that this is minimum power here, this minimum positive power. Okay, power of A such that this A power M belongs to H. And we claim that this H is actually generated by this A power M. We will try to prove this. So since, first thing, note that since H is a subgroup, if A power S belongs to H, then A power minus S also belongs to H. The same argument which we did earlier in case of where we solved the problem related to this subgroup, checking subgroup of A power N sort. Similar argument, A power S belongs to H, then A power minus S belongs to H. That is there. That's not a problem. That's not a problem. I mean, that's property of H being subgroup. Okay. So suppose some A power T, suppose A power T belongs to H. Okay, for some T. T positive, we can take this T positive because once T negative is there, its positive power will also be there because if T is negative, then A power minus T will belongs to H. And in this case, this minus T will be positive. So we'll start with the T positive. Without lots of generality, we can assume this T to be positive. So this A power T is in H. So T, we can then write it in this form, right? Some MQ plus R where this 0 less than equal to R, strictly less than M. We can write this. So we are just doing this division with respect to Q for T. So note that, so A power T is in H, A power M is there, A power M belongs to H implies A power MQ also belongs to H. And once I have this A power minus MQ also belongs to H, okay? So this implies what? A power T into A power minus MQ belongs to H. This implies this A power T minus MQ belongs to H. But this is what? This is A power R which is belongs to it with 0 less than equal to R less than equal to M, strictly less than M. But note that this R less than M is not possible as it will contradict the minimality of M. We chose M to be minimum power of A which belongs to H. Okay, so therefore R has to be 0. So this implies this A power T is actually A power MQ. So this is A power M into Q. And this A power T in H was arbitrary. So therefore H is generated by this A power M. And why we can say this, that is A power T belongs to H, because this A is also a generator of group G. So any element of H is also an element of G. So, and elements of G are powers of M. So that's why this is because G is cyclic. G is cyclic. All the elements of G are some power of M. Sorry, some power of A. And H is a subgroup of G. So H anyway contains elements from G. I mean, H is subset of G, so it has elements from G. So it will also be of the form A power T for some integer T. So that's why we can start with this kind of element. A power T belongs to H. Please understand that. Okay, so that's why in general, any subgroup of a cyclic group is a cyclic. So that's why take any H1, H2, which are cyclic subgroups of G. The new subgroup generated by this H1 and H2 will anyway be cyclic because it is a subgroup of a cyclic group. Any doubts here? Therefore, H is cyclic. Now the third part. So this one is true. Now third, that if GCD of H1 and H2 is 1, then intersection of H1 and H2 will only have identity element. Let me take this. If GCD of order of H1, order of H2 is 1, then H1 is 2 is E. I mean, this. Any This is true or false? What is your guess for this? Again, we will do this, right? Since GCD of, let order of H1 be M and order of H2 be N, the cardinality of these groups. Okay, so if see, clearly this E contains in H1 intersection H2. That's not a problem. Both of them are subgroups of G. G has E, H1, H2 both has E. E is contained. So now suppose some A belongs to this H1 intersection H2. This implies this A belongs to H1 and A belongs to H2. This implies this order of A will divide order of H. Order of this A will divide order of H2. This is because A is element of H1, H2. Order of A will divide order of H1 and similarly. So these imply that order of A will also divide the GCD of M comma N, right? Is this true? This is true, right? This is true. You can check this. This is because GCD is for any given M and N. GCD of M comma N is some integer, this integer combination of this M and N. And this too, and if some D divides M, D divides N, then D will also divide this alpha M plus beta N. This is property of division of integers. So this implies order of A will divide GCD of this H1, H2, which is 1, right? So order of A divides 1. So this implies order of A is 1, and then A becomes identity. Identity element is the only one who has order 1. Okay. Any doubts here? Okay, great. Now the fourth one. So this one is also true. This statement is also true. Now we have to see whether we always have that H1 H2 intersection is always E. So can you give me example where that's not true, or whether this is always true? That statement is we always have, let me write this out. We always have H1 intersection H2 identity. Is this true? Can someone give me some example where this does not hold? Or is this always true? Always intersection of two subgroups of a group is always is identity. See, this is not true, right? I mean, we can have, H is a G is a group. It has H1 to be subgroup, And I can, since this is also a group, I can take a subgroup of this, and this still will be subgroup of G. So this H1 and H2 will be subgroups of G, and their intersection will be H2, and this need not be equal to E, right? And this is the main idea which we will be using here. And for explicit example, we can choose this. Let G to be Z comma plus, okay? And H1 be this 2Z, and H2 be this 4Z. Then what will be this H1 H2 intersection? 4Z, exactly 4Z, okay? Their intersection will be this 4Z. Oh yeah, and in general also, I mean, these are only two examples which I chose, but you can take any integers not equal to 1 here and see that this intersection will always be something not equal to identity if I take this. I mean, and this is also good exercise to check what exactly the form of this H1 intersection H2 will be. Okay, AB not equal to 1. I mean, you can take those to be equal to 1, but their intersection will again will be the same group. Okay, if I take one of the H1 to be G, so G intersection H1 is always H2. So if I take H1 to be G, then this will always hold. This is also one thing which you can keep in mind. Okay, and so this is not true. Okay, this is not true. It will be in some cases, but not always. And here, I mean, see, this will hold only if GCD of their cardinalities is 1. This statement should we prove. I mean, that is only sufficient condition. That's not necessary, but yeah, I mean, we can find examples where, I mean, this is the example where the GCD is, sorry, not GCD, the intersection is not equal to identity. Okay, so now this question 5. This is question 5. This I wrote this is a question 4 actually. Yeah. This question 5, that which of the following statements are correct or true? Okay, so first one is that if x and y are odd integers, then x square plus y square is divisible by 4. 4 doesn't divide n square plus 2 for any integer n, and there exist, third one is that there exist positive integer x and y such that GCD x comma y is 3 and x plus y is 100. Please see whether you find any counter examples or see that, or whether you find any proof for this statement. So this statement is that if n is odd, then n square minus 1 is divisible by 8. These are the statements which we have. So any guesses for this? First one, whether it's true or not. If x and y are odd integer, then x square plus y square is divisible by 4. I mean, yeah. So x is odd, so x is some 2m plus 1, y is some 2n plus 1. So x square is of this form, right? M square plus 4m plus 1. Y square is 4m square plus 4n plus 1. And what their addition is, x square plus y square is 4m square plus n square plus 4m plus n plus 2. Okay, so this divides 4, this divides 4, but this need not divide 4. Okay, so this 4 does not divide this 2. And to see explicit example, what example should we choose for this to happen? Let m be 3, so not x be 3, y be 5. And what's the square? 3 square is 9, 5 square is 25. Oh, in this case it is. So let us choose 9, and what it will be? 9, 81, 90. And 90 is not, 4 does not divide 90. Is this okay? I mean, there always be identity element in this. Yes. So yeah, sorry. I just saw your query now. Always we have this intersection is equal to. I just saw your doubt in the chat. This is equal to. This is always there. That identity is always contained in H1 intersection H2. But what they are asking is for equality, whether this H1 intersection H2 is equal to identity or not. Okay, so that's the question they are asking. This is not true. I mean, it could have elements many more than the identity element. Identity element will always be there. Take any two groups, not any two groups, any two subgroups of a group. Their intersection will always have identity element. Their intersection will always have identity element, but that intersection need not be equal to the identity entirely. For example, this. Definitely this contains 0, the identity of Z plus, but this is not entirely equal to what the intersection exactly is. Om Prakash, is this okay? We are asked about the equality. The equality needs to be there. I mean, the other way around, in equality should also be there. I hope you are there. Okay. So yeah, the containment is definitely there. What you said is about containment, and yes, identity element will always be there, but it, I mean, the intersection is not exactly, I mean, the intersection need not be equal to the identity element entirely. It may have many more elements like this here in this case. Okay. Oh. So yeah, here this, if x and y are odd integers, then x square plus y is divisible by 4. No, it need not be true always. And this is the example which we got here. Okay, for this it is 4 doesn't divide 90, right? This is 45 into 2. So 4 doesn't divide this. Now, next question. This is false. Now B part, that 4, let us see. 4 does not divide, 4 does not divide n square plus 2 for any integer n. So let us do this thing. For even n is equal to 2m. So n square is 4m square. So therefore, and 4m square. So if this m is even, then this 4m square is some, let me write this 4m square, not n square, let me write 4p square. And otherwise, or if m is odd, p belongs to z. Otherwise, it is of this form, right? 4p square plus 4p plus 1. M odd, p in z. Okay, in both the cases, this 4p square plus 2, I mean, 4 need not divide this. Okay, I mean, 4 does not divide this 2. And secondly, for odd cases, this is 4p square plus 4p plus 1 plus 2. So this is, this won't hold. Okay, this is 4. I mean, this 2 will always create a problem. Wait. Yeah, wait, the question is different. This 4m square. Yeah, 4p square and then 4, wait, for, so in both these cases where it is even, this 4 does not divide 4. 4p square plus 2 and 4 will not divide this 4, 4p square plus 4p plus 1. Okay, because plus 2. Here it will be 4p square, p square plus 4p plus 6. Or again, this is 4 plus 2. This won't happen. And again, if for odd numbers, if n is equal to 2m plus 1, this n square is 4m square plus 4m plus 1, and for this n square plus 2 will be 4m square plus 4m plus 3. 4 anyway does not divide this 4m square plus 4m plus 3. Okay, is this? Or in even case, we will do it. I mean, forget about this. This is very confusing. In even case, we can simply do this. If n is even, so 4 divides n square, right? 4 divides this 4m square, right? So if 4 divides n square plus 2, this implies 4 divides this 4m square plus 2. So, but using this 2, this implies 4 divides 4m square plus 2 minus 4m square. This implies 4 divides 2. This is contradiction. So, therefore, 4 does not divide this n square plus 2. Similarly, we can do the same thing here. Okay, it will boil down to the condition that 4 divides 2. That's not true. I mean, it won't. In case of odd, it it's directly clear that this here is true. So 4 does not divide 4m square plus 4m plus 3, because we know that 4 divides 4m square plus 4m. So if 4 divides n square plus 2, this implies 4 divides 4m square plus 4m plus 3. But 4 also divides 4m square plus 4m. So this implies that 4 divides their subtraction, which is 3, which is again a contradiction. So that's why this is true, that 4 does not divide n square plus 2 for any integer n. Okay, for n is equal to 0, this anyway holds. So 4, wait. N is equal to 0. N is equal to 0, 4. I mean, n is equal to 0, we don't have to consider. I mean, yeah, for n is equal to 0, 4 anyway does not divide 2. So that's there. Let me write, for n is equal to 0, 4 does not divide 2. So even and odd, we have it here. So I hope this one is clear. Now the next statement. Next statement is that C part, that there exist positive integer x comma y such that GCD x comma y is 3 and x plus y is 100. What is your guess in this case? Is this true? It's false. See, GCD of x comma y is 3. This implies that 3 divides x and 3 divides y. Okay, and if that is the case, if such integers exist, if such integer exists, or integers exist, then 3 will also divide x plus y. That is, 3 will divide 100, which is not true. Okay, so therefore no such x and y exists. Okay, I hope this is clear. This is directly a GCD of elements, and we got that this is not true. Now the last one. This one is not true. Last one is that if n is odd, then n square minus 1 is divisible by 8. Let me just write this statement. If n is odd, then n square minus 1 is divisible by 8. So any guesses whether this is true? So given that n is odd, let n be odd. So n square is what? N is what? Some 2m plus 1. This implies n square is this 4m square plus 4m plus 1. Now we have to check for 8, whether 8 divides this minus 1. So see that if this m here, if m is even, then m is some 2k. So n square is equal to 4k square plus 4, sorry, yeah, 4k square plus 2k plus 1. Okay, so 8 definitely divides this, right? So 8 will divide this 4k square plus 2k. Okay, so that's why it will divide this n square minus 1. Therefore, n square divides n square minus. Therefore, 8 divides 4k square n square minus 1 for n of the form 2m plus 1 where m is even. See, from directly here we can't conclude that this is divisible by 8. From here, we can't directly conclude. From here, we can't conclude directly. Because if this m is odd, then this 4m need not be multiple of 8. Okay, if this m is 1, then what will you do? I mean, this statement is true. So even for odd statements, it's true. But from here, you can't say this 4m is divisible by 8 or not. This 4m square is divisible by 8 or not. I mean, we can't directly guarantee that thing. So for example, if I take 5, then 4 into 5 square, 4 into 5 is 20. I mean, 4 into 5 and 4 into 25 here. We don't really know what exactly is happening in that case. Or do we have any better? Oh, or we can directly do this. Forget about this. We can do this. See, what is this? N square is 4m square plus 4m plus 1, right? So we can write this as 4 into m square plus m plus 1. So this is 4 into m plus 1 plus 1, right? So, yeah, I mean, from here we can directly conclude this. I mean, after this, some simplification. So now n square divides this 8, divide this 4m, m plus 1 for n square minus 1 is 4m, m plus 1 minus 1, right? So this implies this is n square minus 1 is 4m into m plus 1. But if m is odd, this implies m plus 1 is even. This will implies that this n square minus 1 is 4m into some 2k. So this implies 8 will divide 4m. And if m is even, then this will imply that n square minus 1 is 4 into some 2k m plus 1. And it is 4 into 2k into m plus 1. This will again implies that this 8 divides. This is not correct. N square minus 1. N square minus 1. Oh, 8 divides this 4m into 2k, and this m divides 4 into 2k into m plus 1. So therefore, in either case, therefore, 8 divides n square minus 1, where n is odd. Okay, so note this. This is the key here. M plus 1. So whatever integer. So m is odd, m plus 1 is even. M is even, m is even, then that's not a problem. But if m is odd, m plus 1 is even. So from here we can conclude that n square minus 1 is always divisible by 8. Any doubts here? We don't need to go through this. I mean, this section is not actually needed here. Can start directly from here. Okay. Any doubts? No doubt. Okay. Now we are almost there. 5 more. One last question. I don't know which question number. I think it is question number. So this one is correct. Okay. Question number 6. Mz plus nz is equal to dz, where d is LCM of m comma n. Is this true? Check true or false. What is your guess in this case? What they are saying is mz plus nz is dz, where d is LCM. So this is always true. So what is LCM of mn? It's false. Okay. So when I write this dz, note that. So it is this 0 plus minus d plus minus 2d and so on. So least positive integer in dz is d. So least positive integer in dz is d. Okay. And LCM in general is something, LCM of two integer is greater than equal to those two integers. Okay, but I mean, this is just very, I mean, we will write the, I mean, we will give the proper counter example, but LCM of m comma n is normally greater than not, I mean, it is greater than equal to both m and n. Okay, so but if I take this m and n to be, so when I said that it is generated by dz, which is LCM of, if d is LCM of m comma n, and if I said this mz plus nz is dz, then note that this 0 m, this 0 plus n belongs to dz, and this m plus n belongs to dz. So sorry, m plus 0 belongs to dz. So this, if if m not equal to n, then one of them will definitely, and without loss of generality, if I take this, then this n will not definitely divide, sorry, does not belong to dz, but it will definitely belong to this subgroup generated by dz. Sorry, n does not belong to dz, but n belongs to this mz plus nz. Okay, so this is just by looking at LCM that this does not hold. Okay, just understand this thing that LCM is greater than equal to both the elements. and this I'm writing here. This is relevant here, not here. This is greater than equal to D. Sorry, this is less than equal, M is less than equal to D. This I hope you understand. This is very bad way, but just understand that this is very huge number. LCM of two numbers will be very huge number. Whereas this group, this subgroup Mn plus Mz plus Nz, it contains both M and N. Okay, I mean, I hope you understand what I'm trying to say here. This is straight away very false. So to give an explicit example, this let M is equal to, with what one to take, which one to take? Let us take M is equal to 2, N is equal to 3, then Mz plus Nz is whole Z, right? Because 1 belongs here. I can take 3 from here. No, yeah. I can take 3 from, I can take 4 from here and minus 3 from here. And their addition, which is 1, belongs to Z. And the moment I have 1 in this group, this implies 1 belongs to Mz plus Nz. This implies that Mz plus Nz is whole Z. Okay, but LCM of M comma N is 6, and definitely this Z is not equal to 6Z. Okay, so the easiest, not easiest, but a quick way to understand this is that this group here contain both M and N. And these and LCM is something which is very bigger than, not always, but mostly bigger than both M and N. Depending on what we are choosing, the same elements which we choose, it's the same thing. And if we take M dividing N, then the smaller one becomes the LCM. But if not, if their GCD is 1, LCM is literally product of those two elements. So which is very uh like which is bigger than both M and N. And this dz when I write, please understand that this is the case here. D is the least positive integer which belong to this set dz. Okay, is this okay with you all, what I'm trying to say here? If not, if this is very confusing for you, just leave it. Understand that this is not true. M is 2, N is equal to 3, Mz plus Nz is Z. LCM of 2 and 3 is 6, and Z is not equal to 6Z. Is this okay? This is false. So this statement is false. In fact, you can take it as an exercise and try to prove that this Mz plus Nz is a dz, where D is in fact GCD of this M and N. Okay, you can try to prove. In fact, in the lecture itself, in earlier, someone said that we have to prove that this D is the list such that the linear combination is giving me D. And that list will be my GCD. And that's how this dz is. Okay, D is actually the least positive integer in this subgroup dz. And that is my GCD of M and N. Okay, is this clear for now? Any doubts, please let me know. Otherwise, if you have any doubt from this or any lecture or whatever we discussed today, If not, please let me know. Otherwise, we will end the session for today. We are already okay. So I assume there are no doubts. If there are doubts, please let me know. Otherwise, I will end the session. Okay. Thank you.